In this tutoring film, we will concentrate about subroutines, one of the major essential components of software program, and we will give examples on 8085 and 8086 microprocessors and their emulators and so on. The summary of the information which will be given in this slideshow, subroutines and their utilization are summarized by using their usage in 8085 and 8086 classical microprocessors, 16-bit and 8-bit versions of these very well-known processors. Before proceeding, in order to fully understand the topics covered, you should have sufficient knowledge about the following concepts. The most important one is binary and hexadecimal number system, 8085 and 8086 microprocessors in general, and specific registers in these microprocessors, namely AX, mostly AX and BX. Of course, CX and DX are also used. In addition, program counter and instruction pointer registers, namely PC and IP. Now we can start with the definition. What's the meaning of subroutines? In many books or software programming languages, other names are given like procedures or functions or subprograms. Those are smaller programs which are subset of the main program in a sequential programming set. Also, subroutines can be used in object-oriented programming as well. In our scope of the microprocessors and associated assembly language, subroutines are defined as a special segment of a program. Well, segment does not mean that it should be 64 kilobyte long. No, segment is a part of the program. A subroutine starts with procedures 4-letter proc and ends with returns 3-letter ret. So between those reserved words, a special part of a program is called a subroutine. So this segment not necessarily 64 kilobyte long, okay? Because a segment of an 8085 and 8086 is a part of the memory which is definitely 64 KB long. Now let's return back to our subroutines. They can be called for execution from any point in the program, any line actually at this point in the program. The advantages of subroutines are as follows. They are very efficient for repetitive tasks. So if you continuously repeat a special task in the program, then define a subroutine and call this subroutine in the program as many as you can. So that saves valuable program length as well. Tasks may be lines and lines long, and these tasks can be called by using the name of the subroutine, a few characters or one word, and that's it. You just call the name and program does the rest. What do we mean by calling a subroutine? There are two ideas behind the subroutine. The first one is you should be able to call the subroutine from anywhere in the program, in the main program. Once the subroutine is complete, it should return back to the place that had called the subroutine. So this is the verbal definition. This is the conceptual diagram. So we have main program here. It's a sequential program, and with lines and lines, it starts, and at some line a subroutine named A is called. At that moment, the computer memory and other digital units align themselves to accomplish the first instruction in subroutine A. Usually this A is written at the end of the main program. Okay, not like in 2 columns of a program. Normally this part is here, because we have only 1 column computer program writing. This program, sequential programming, executes the first instruction and continues till it hits the return or ret here, then returns back to the next line which had called this subroutine, and this is called again next instruction, continues. At some other points in the program, next call is encountered. Again, program digital media aligns itself for the new execution, repeats the same thing till its return, and goes back to the program. So many times you can call a subroutine and do the many tasks, multiple tasks in one line. That's it. So there's a better, or definitely a computer code line save in writing a program. So these are also modular. You can copy and paste to a different program, so you save a lot of computer program writing time as well. A simple example. What does it look like in an emulator environment with assembly codes? This is a sequential main program. The first line organizes the program segment block to be 0100 hexadecimal address. The program starts, and the first instruction moves a decimal value of 2 to 16-bit register AX. Then some subroutine called M1 is called. At the same time, the program goes to this block, which is the subroutine. The name here, and this is the first line, so it designates that this is the procedure named M1. That procedure is very simple, 1-line procedure. It just adds 2 registers and stores the value of the result to register BX. Then it returns back and it increments the register A. Then the same subroutine is called, tasks are repeated, returned back to increment AX. Then the same subroutine is again called for the 3rd time, same tasks are repeated, and subroutine is ended. So we return back to the main program, to the next line, which is about to increment the value of AX, and the program halts to the operating system, stops there for any user interface, etc. So instead of writing, okay, if we had 1 line, this program is not a very good example of saving programming time to write subroutines. But if we have multiple lines here, instead of writing the same thing for 3 times, which consumes programming memory space, we just consume only 1/3 of it for this example. So what happens when we use an emulator? We write the same program to the editor screen, and then as soon as we run the program, the first line, which is the move AX 0002 hex X, is being executed. In the next line, and one procedure is called like this, then program jumps to another point in the memory space to execute the subroutine, then comes back to the next line and then goes back to the subroutine line again. Okay, this subroutine is written in the physical address of 0110 hexadecimal, which is not shown here because we see only addresses 7100 here. So this program is in hexadecimal codes or assembly codes, very simple to be understood. Now what happens after the call instruction? Main program execution continues from the address of the subroutine specified by the operand, and information required to return back to the main program, such as instruction pointer and code segment, are saved on the stack. These are necessary for the program after the subroutine wants to return back to the original point that calls the program. So these are the next line information: code segment plus instruction pointer. So the components of subroutines are: 1, an entry point, which is called this one, the location of the first instruction in the routine. Then parameters, the list of the registers or memory locations that contain the parameters for the routine. Then return values, what are the values are returned back to the main program registers after completing the subroutine. And working storage. This is the memory space allocated for the subroutine only. It should not and does not intersect or overlap with the main program storage area, otherwise conflicting or crashing occurs. We have another example, but I hope it can be read in the screen. We have some headers for the program, some move instructions and 3 call instructions, then again move instruction and an interrupt instruction. This is a little bit more parameter, more versatile program. So the first call, subroutine 1, is named as the entry point for subroutine 1. Subroutine 1 is written in this block. There may be many lines of it, and usually it's a good habit, it's not required, but it's a good habit to have some lines or breaking system that this is the main program, this is the subroutine part, so one can easily see what's going on here. So at the end point, okay, at the return command, it returns back to the main program. The end line, subroutine 1 end procedure, is the so-called like footer of the subroutine. So the compiler understands that this is the last line of the associated subroutine named as subroutine 1. And the next line, there's a call for subroutine 2. Subroutine 2 is here, and the next line, subroutine 3, all do have the same type of format between 2 lines, 2 horizontal lines. Those lines are commands, so compiler does not give any error. So at the end of the subroutines, main program subroutines, we have an end for the main program. So this is a typical example of good programming habit for a 8085, 8086 assembly code writer. Now we come to another concept related to subroutines. This is called nesting. Nesting means simply one subroutine calls another subroutine inside that subroutine. In this case, the return address of the second call is also stored in the link register, destroying the previous contents. Hence, it's essential to save the contents of the link register in some other location before calling another subroutine. So, in this case, the program should track to return back to the correct address. So, each program can nest up to a maximum number of subprogram calling or nesting values. Usually, the number is 8 for our case, but they can be more or less. So, as a good programmer, usually do not nest more than 3 or 4 subroutines. In nesting, the call instruction is a special branch instruction. So the program jumps to another line, it is a branch, and performs the following operations. First, push the contents of the program counter or PC register on top of the stack, update the stack pointer, branch to the target address specified by the instruction. The return instruction is a special branch instruction that performs the following operations. So these are two main headings. This is the reverse. So this is the calling, this is the returning part. In the return part, the return address information is popped from the top of the stack into the program counter, and stack pointer is updated. For example, a conceptual diagram of a nested subroutine. We have a program portion called P. Inside P, we have two calls, subroutine R and subroutine Q. So P, subroutine R, and subroutine Q. In the first moment or occurrence, the subroutine R is called, so the program branches to R. So we have R and procedure, etc., and after return R and procedure lines are omitted, so conceptually. So in the first jump, it jumps to here, performs the operations, then it returns. After the return, it jumps to the next line, which is the Q. The next line is calling Q subroutine. Q subroutine is here. While performing or executing the instructions in Q, there is a call R. So from P to Q, we have R. So this is a nested subroutine. Calling R is not nested because simply it's back and forth, only one loop. But in nesting, we have two loops. After R, it's returned in the fourth one. Okay, in the third one, call Q, calls Q. Inside Q, R is again called, and this time return from R is not to the main program, but to the next line, which is calling R. So this is number 5. Okay, number 1, number 2, number 3, number 4, number 5, and after returning, number 6 returns to the main program. So this is a very good and basic example of nested subroutines. P is the main program, Q and R are nested subroutines. An assembly line for 8085, 8086 or emulator 8086 program can be like this. P and R and Q may have some values moved or stored in AX, BX registers. R can be something here, adding something, doing some operations on these registers. Q is nested subroutine pair. Okay, from P calls Q, Q calls R, R returns back to Q, Q returns back to P. So it's from the editor screen can be decoded like this. And if you write the same program to emulator editor screen, when we run the program, we can follow the nesting, etc. by the same order that I have described. There are mainly two types of calls of subroutines. One is called near call. The other one is called a far call. Those near and far are related to the points in memory. In the near procedure, call instruction and the subroutine it calls are in the same segment. So their addresses are within 64 kilobyte memory space. Then it saves the only current value of the IP. So since they're in the same segment, there's no need to change the value or to store the value in the segment register. So we only change the offset register, which is the instruction pointer on the stack. Then the subroutine's offset value in the IP for the next instruction. And the example is the same as previous examples. We have subroutine 1, which is a procedure. The address has some commands, and it has other instructions and return and end of the procedure. So into the stack, the values associated are stored for the instruction pointer. In contrast, far procedure, the call instruction and the subroutine it calls are in different segments. Therefore, there is more than probably 64 kilobyte memory spacing between the call point and the subroutine itself. So the current value of the code segment should also be saved when returning. This is the only difference. The others are the same. So in the return, code segment value is popped back from the stack. So in writing, the far word are added. So in this case, code segment and other related segment information are also stored. We have bunches of elements in different related to different values stored in the stack for near and far calls. This is again another value storage in a stack, but this time this example is rarely found. The addresses usually are expressed from lower to higher, from bottom to top. This time is the reverse order, from the address 002 to the maximum value here, okay? And little endian is low byte at low address, but low byte is not at the bottom, rather it's at the top, for very well-known or widely used one in contrast to those. So in the stack, for example, these two 16-bit registers are stored in little endian convention, so that 16-bit information is stored in two consecutive 8-bit registers. In this case, instruction pointer and related to data register BX, for example, are stored as shown. And in the textbook, well, I hope you can read them, but basically stacked during a near call and far call are compared in the memory maps. The only difference is everything's the same, including the parameters, instruction pointer values, etc. Code segment values are stored in the far call, which can be seen. An additional 16-bit memory space should be allocated for this in the whole memory map. All this information have been compiled from various internet and textbook resources, including some university slides and definitions, etc. So we acknowledge contributions from these references, and special thanks to Tuğba Demir, who had done preliminary slide preparation, and they were all finalized by myself. Narrations and all explanation errors, etc. belong to me, and the films are prepared by myself, and all the equipment infrastructure have been generously supplied by my university. And if you can send some comments, please feel free to send me via email to this address.